CPUs. In this nugget, we talk about CPUs. And by the way, because I'm an old English major and kind of a grammar snob, I'd like to point out that it's not CPU apostrophe S. It's not a possessive, and it's not a contraction. So it's just CPUs, and I'm kind of making it a plural, even though it's on the end of an acronym. Okay, so maybe there's still something wrong with that English. But anyway, what we're going to talk about here, first of all, is the architecture of a CPU. What kind of process the data goes through when it goes up through a CPU and where it goes. We'll also take a look at various characteristics of CPUs that'll be important for you to be able to identify, and which will help you to identify which needs a customer might have. And then we'll talk about upgrades, which is closely related to the architecture and characteristics. You can't upgrade something if you don't understand the characteristics of a processor, so we'll look at that, as well as the various technologies such as hyper-threading and microcode instructions and things like this. And then finally we'll take a look at sockets. It's really slots and sockets, but most of the time we just use sockets these days, and I'll show you the common kinds that are in use. Now, before we get too far along in processors, it's going to really help you to understand some of the other technologies and terms if we first of all look at the flow of data from within a processor so we can understand how things work. This will not appear on the A+ exam, but bear with me if you will for a few moments, or a few minutes actually, because this is going to help you to understand some of the other things. Now, first of all, notice that this is probably just about the ugliest picture of a processor you've ever seen. It doesn't have a fancy logo that says Intel or AMD or any of that. It's just a logical diagram, and they don't actually look anything like this. This is just a logical flow of the data which comes in through an I/O unit. This is also known as the front side bus or external data bus to the rest of the system. So whatever the speed is of this front side bus or external data bus, it must be matched on the motherboard, and it has to be rated at the same speed, whether it's 800 megahertz or whatever the speed is, in order to get the maximum performance out of your processor. If my processor has 800 megahertz front side bus, but my motherboard only supports 400, well, I've shorted myself some performance there. Now this I/O unit is also 64 bits wide. So we have a 64-lane highway for data to come in and out of this unit. And this is just kind of the front door or the gate. And there's you can kind of think of racing horses, Churchill Downs. How all those horses are behind the gate, and then the bell rings, and I don't know how many of them race at a time, but maybe a dozen of them come out at the same time. Well, this is the same kind of a gate. It controls the data going through here, just like when it opens up and allows data to go through, just like a gate opening for one of those horses. And then once the data comes into the processor, it's handled by something else here called the control unit. Now, there's still 64 bits of data all the way up through here, in through the I/O unit and in through the control unit. But at this point, the control unit splits it into two, so we're going to have it divided between two arithmetic logic units. There's going to be 32 bits of that 64-bit data path over here, and 32 bits are going to go over here. And this effectively, for modern processors, is going to be pretty typical. Almost any processor that's modern now will have two arithmetic logic units. And in fact, if you look at certain monitoring processes or little applications that monitor the performance of your processor, it may actually show two processors. And you might think to yourself, doggone it, I know my motherboard only supports a single processor, and yet something shows me that there's two of them in there. I'll give you a good example of that right now. If you want to look at Task Manager, this will tell you how your system is performing. I can right-click on the taskbar and choose Task Manager. Now I can also press Control-Shift-Escape on the keyboard, or hit Control-Alt-Delete, and there will be an option there to find the same thing. And here we have the CPU usage right here. Now notice that it shows me two processors. What am I really seeing there? You guessed it, ALU1, ALU2. So those are the two arithmetic logic units that I'm actually seeing there. And that's really pretty much the core brains of your processor. The arithmetic logic unit is what does mathematical calculations and comparisons, and if something compares one way, it knows that the data is true. If it compares another way, then it knows that something is false or off or one of those kinds of things. So that's where all the complicated arithmetic logic takes place. Now, while it's working with the data, it's kind of like my kids with homework. They might come home and they'll have long division, and they'll say, Dad, can you help me with my long division? And I kind of halfway pretend as if I actually remember how to do all of that stuff. And so while I'm trying to help them, I have to write in scratch paper off to the side, what times what equals 128 or something like that, to try to check all of my math while I'm going along. Well, that's what this register does up here for each arithmetic logic unit. It's kind of a scratch area where it holds all of the calculating data that it's having to work with. It's its current working set data that happens right there in the registers. And then there's another pathway that we have here, and you may have heard this in computer stores and so forth. It's something that's called the backside bus. And the backside bus is connected directly to the arithmetic logic units and to the control units. Now, when I talk about cache, I'm talking about level 1 or level 2 cache. And before I get into the distinction there, let me first of all point out that the cache, regardless of what level it is, it's a portion of memory. It can be a few megabytes in size, and it's a calculated guess as to what the ALU is going to need next. And the control unit is capable of determining what should go into that cache. So, for example, if the arithmetic logic unit has performed the exact same calculations a few times in a row, then the control unit might guess that it's going to need that same calculation data again in the near future and put that data blob right here inside of the cache. That way the ALU doesn't have to go all the way out to the system bus and then back out to the system memory to retrieve it off of my memory modules. Instead, it can just retrieve it directly off here off of cache, which is substantially faster. And then you may have also heard of level 3 cache. In the old days, level 3 cache was actually stored on the motherboard somewhere. So you might not even have a processor installed on the motherboard yet, but this level 3 cache would be there waiting for the installation of a processor, and then it would be used when that processor was installed. A level 3 cache can still be off die or still be off package. But nowadays, it's more common to have level 3 cache on the die or actually in the package the same way that level 1 and level 2 cache are. Now, level 3 cache will still be further away from the ALU. Electrically and logically, both the nearer caches are actually going to perform faster for the ALU. So the level 1 cache would be closest, the level 2 cache would be the next closest, and level 3 cache would be the furthest away, but still, again, in the same package as the processor. And to further blur the distinction between all of these, sometimes nowadays the level 1 and level 2 cache are going to be on the same die as the processor, and it's almost indistinct in terms of which part's level 1 and level 2. If you have that kind of a situation, that's frequently referred to as the Advanced Transfer Cache, or ATC. The ATC bus is 256 bits wide and runs at the same speed as the processor. So ATC cache is very, very fast. And then for 64-bit processing, for our internal data bus, which is normally 32 bits, that now would be 64 bits, and that's what makes it a 64-bit processor. And our 64-bit processors also usually have 2 arithmetic logic units. And then this part out here, instead of being 64 bits wide, guess what? Of course, it's going to be 128 bits wide instead. Now, of course, just as a side note, if you do use 64-bit processors, then you're going to need totally different drivers for all of your hardware, all your peripherals, your cards, your RAID cards, your printers, all those sorts of things. You're going to need 64-bit drivers because they're going to be coded differently than a 32-bit driver. Now then, just to review our various buses here, I've kind of drawn these in here for us. Remember that this 64 or 128-bit data path to the I/O unit is known as the front side bus or external data bus. This bus here, where we have data that goes to and from our arithmetic logic unit, from the registers and from the control unit, this portion, and I'll just draw arrows this direction, okay, this portion here is going to be known as your internal data bus. And that's normally going to be 32 bits wide, but 64-bit processors are going to have 64 bits wide. And then over here, our bus width between the cache and arithmetic logic units and control unit is going to be known as our backside bus. So then with all those things in mind, let's take a look at some CPU characteristics, and we'll start off here then with core speed. I think it's in here somewhere. There it is. Core speed. This talks about the speed that's taking place where all this data is running around inside of the processor within this. That talks about how fast that's going. So for example, if it's a let's say 3.2 gigahertz processor, that means it's processing data or executing 3,200,000,000 clock cycles per second. By the way, that's more times than the human heart beats in a lifetime. So it would give you a sense of scale there. That's an awful lot of data that can take place within just 1 second inside of that processor. Now, that speed, and that's how we usually refer to our processors. I want a 2 gigahertz processor, a 3.2 gigahertz processor, a 4 gigahertz, and you get the idea. That's what we ask for when we're buying one of these processors. It'll also have a system bus frequency for our front side bus or our external data bus. Remember, this portion right here is what's actually going to interface with the motherboard, and that motherboard might only be capable of operating at 800 megahertz. So you still have to be aware of that system bus frequency that takes place out here, because that may have an effect upon how fast the processor is able to calculate and actually get data to a useful location. And then I really already addressed this in the previous diagram there, but we have our front side bus or external data bus. Remember, they're the same thing. And we rate that in speed megahertz. That 800 megahertz is a pretty good performer right now for current motherboards. They can also go up to 1066 megahertz. And those speeds are always climbing, just like processors are always climbing as well. So those are some common speeds that we'll see out there. And then the data path, which is that bit width that I mentioned earlier, 64 bits for 32-bit processors, or 128 bits for 64-bit processors. And then remember that, again, our cache can operate on a level 1, a level 2, or a level 3 cache. Level 2 or level 3 cache is usually larger than level 1. For example, level 2 might be 1 megabyte, might be 2 megabytes. Some servers might even have up to 4 megabytes. And the level 1 might only be 512K. So usually it's smaller, but again, with advanced transfer cache, that kind of gets all mashed together anyway. And then we also have multi-processing. Now, first of all, realize that the operating system must support multi-processing if that's what you want to do. Just about every current version of Windows does, so that's not really an issue for us the way it used to be back in the days of like Windows 98, because Windows 98 would not support multi-processing. But what has to happen is you have to have a motherboard like this one that supports 2 processors. There's a processor underneath this giant heatsink over here. We can't really see it. But then notice that this one is empty because I haven't upgraded this server yet to have 2 processors. And of course, I've got this shroud here that for the air duct airflow to go through here as well. That's what's covering everything up right now. But because I'm running Windows Server 2003 on the server that we're looking at right here, it supports multiple processors. It supports 4 processors depending on the version. Some of the other more expensive versions of Windows Server 2003 would support up to 8 processors or more, in fact, depending on how it's configured. Now, of course, the server products are a little bit out of our scope, but Windows XP would also support this. If I just formatted the hard drive and installed Windows XP instead and put another processor in, yes, it would also be able to support both those processors. Now, when you do that, be aware of the fact that you may also need to put a special card in here for the voltage regulator module, and that will help to equalize and share, rather, the processor, the voltage between these 2 processors and make them play nice with one another. Other usages for a voltage regulator module is so that you can adjust the performance of a processor so that even in a single processor system where there is not support for dual processors, you might still have a VRM, again a voltage regulator module, that adjusts the power to the processor. Now, as you might guess, if I add another processor in here, I'm essentially adding another brain to this computer, because this whole thing right here, this really is the brains of your computer. That's what's doing all of the thinking and the calculations. So by adding another processor here, I've pretty much doubled the intelligence of this system. Now, just imagine that. If I had 2 brains, wow, I might have an IQ of like 100 or something. Actually, it's kind of strange because maybe it's a gender-specific thing, and I hope I'm not sounding sexist here, but it seems like my wife is able to process multiple things at once, whereas I'm always stuck on one processor no matter what. She seems to have like 3 or 4 different processors going at once. She can talk on the phone to her friend while she's watching television in the kitchen, getting dinner ready, and helping my kids with the homework. I don't know how she does it all. It would drive me insane. Some people are just built to multitask that way, I guess. Now, also, as I go back to this, remember that we really have 2 arithmetic logic units, and that's what gives us the effect of 2 processors in our CPU usage right here. If I added an additional processor, and incidentally, this picture right here is the computer that I am working on right now that I'm using to record this video. All my video, for example, is going through this processor underneath this heatsink. Everything's taking place right there as we speak. Now, if I were to upgrade this to another processor right here, which Windows XP would support and which I'm running, then our task manager here would actually show 4 processors here instead. And that's just the effect of it. and it would substantially increase our performance by doubling our processing power. Now, you might be a gaming enthusiast or someone that just likes to have the hottest, fastest computer, but you don't have a motherboard that supports multiprocessing. By the way, those motherboards are substantially more expensive generally than just your single processor motherboards. So what are we doing to get around that? We're buying dual core processors. And any of the Pentium processors that have a D in the name. For example, it might say something like Pentium D950 or something like that. Anything that has a D in it means dual processors or dual core on the same die. So I get a package that will fit into the same kind of a size slot or same size of a socket as any other processor would, but guess what? The density of it is twice what it would otherwise be. That's another way of talking about processing power is the density. That means I'm fitting twice the processing power in the same size package, and now I'm using a single socket on my motherboard, but I'm getting two processors there, both of which might have two ALUs. So again, I'm going to have the situation where I have effectively four processors all working at one time. And then we can add to that fact that you might have quad processors now, which Intel at the time of this recording, is recently releasing. So in a single package for a single socket on the motherboard, you could effectively put four processors into that one space. So this also goes to our CPU upgrades, because if you want to improve the performance of a system, you can think about that multiprocessing that I just talked about. If you got a motherboard that supports two processors, you might drop another one in there. Intel Itanium processors, for example, would support that, as well as Intel Xeon processors, which is spelled Xeon. This also supports multiprocessing, and that's the kind of processor that was in the picture that I showed you that was underneath that heatsink. Or you could use the dual-core processors in a single socket like I just mentioned. Quad processors are something that's on the horizon and that's recently released, but that's not part of the A+ exam objectives. You can also take a look at your motherboard specs. Again, take a look at the front-side bus speed of your motherboard, because if it's too slow, then you might not be able to get the effective throughput for all your processing power that the processor is capable of delivering. Another big part in the motherboard specs is going to be the speed of that front side bus. And I alluded to that a little bit earlier. But if I've got, say, a 800 megahertz front side bus, and I got a 3.2 gigahertz processor, then what I do is I can calculate that out and determine my processor frequency. So 800 megahertz goes into 3.2 gigahertz how many times? 4 times. So that would be a multiplier of 4, which would be my 3.2 gigahertz. I'm going to run it out of space over there, but you get the idea there. So this also takes into something else that we could do called overclocking. What if my motherboard supports it, and most of them do these days, then I could overclock this. So I could go 800 megahertz, and then in my, usually it's going to be in the system BIOS, but could it also be done through dip switches or jumpers, especially on older motherboards? I can, instead of multiplying that by 4, I could say, hey, I'm going to cheat the system, and I'm going to multiply it by 5. I'm going to overclock this processor now, and that's going to give me 4.0 gigahertz instead. So I didn't have to run out and buy another processor at a higher performance. Instead, what I did was I just cheated, and I upgraded I changed my system BIOS to reflect a multiplier of times 5 instead of times 4. Now my processor, right on it, and with the instructions that come with it or the specs, it'll say that it's designed to only go at 3.2 gigahertz. If I go to 4 gigahertz, then I can void my warranty, but a lot of gamers or extremists with computing here will deliberately do that. The upshot of this as well is that because there's a much higher processing power going on in that, I'm going to get hot processors, and I'm going to have to get bigger heat sinks or more effective heat sinks or maybe a liquid-cooled system to make sure that I don't burn out my processor. Now, for a multiprocessing scenario, you also have to consider the stepping, because I might have two processors in my hand that I want to install somewhere, and they might both say they're Intel processors, Intel Pentium 4, running at 3.2 gigahertz. But guess what? They might not be exactly the same. One might have more cache than the other. One might have more level 2 cache. One might have more level 1 cache than the other. So there are slight variances, and if you look at the stepping on the processor, which is a code that exactly identifies that specific processor, then they must match exactly. And then don't forget, again, your voltage regulator module might have to be adjusted as well if you upgrade your processor or if you add another processor in a multiprocessing scenario. Now then when it comes to cooling, we have two different kinds of cooling that can take place. The first one is just passive. So for example, if I had just a heat sink like this with no fans blowing directly on it, that would be a passive heat sink. Now there are other variations of this kind of thing where there's no fans on the heat sink. It just allows heat to dissipate through these cooling fins. Don't see those very often anymore. Most processors run hot enough where we need to supplement them with some kind of a fan. So if there's no fan, that would be just something we call passive. If we have active cooling, then that would include fans, which can blow directly on top of the heat sink, or you might use liquid, and I talked about those in a previous nugget. All right, let's also take a look at some of the CPU technologies, and these will be terms that will be very important to understand for the A+ exam objectives, and we'll start here with hyperthreading. Hyperthreading is this, where we have two arithmetic logic units operating at once. It's the ability to perform two sets of data execution in parallel to one another. So that's also what's going to give us this right here, where it looks like I've got two processors. That's hyperthreading. It's able to run two threads of processes, if you will, at the same time. And so that's what we're going to do. We're going to get that performance increase because of hyperthreading. And then we've also addressed this before, dual core or quad core, where we take, again, our little picture here. This would be a single core, but a dual core, we would multiply all of this times 2. And a quad core, of course, we'd multiply all of this times 4. So that, again, is where we get a higher density level for the same package size for whatever our processing unit is. Then we also have something called throttling. Now, this actually has two separate kinds of interpretations. One of those is that the processor, if it's running too hot because it's performing too many calculations at once, it can throttle down and reduce its calculations per second, and then therefore make itself run cooler. That's one form of throttling. The other form of throttling, which is also known as clamping, is controlling how much CPU time is allowed for each application. And it's just an effort by the processor to make sure that all the applications get the same level or a fair level of CPU time. And the CPU time is divided up into something called time slices, and so it just divides that pie up into equal parts or fair parts for each application depending on their priority. And then microcode is a bunch of data that has something in common. So for example, with Intel's MMX data, that would be an instruction set that had multimedia in common. That's multimedia extensions. That's an Intel-based kind of a function that takes place. So an MMX processor would have some logic unit within the processor that would handle multimedia instruction sets. And it would then offload a lot of the processing power that the CPU would normally have to perform, and it would instead be handled by the MMX portion of the processor. And it would be dedicated to multimedia, and it would offload that kind of a data burden from the main CPU. And then we also discussed overclocking already, but I just took a screenshot of overclocking on one of my computers around here. Just use a digital camera, take a screenshot of it. You can see how you can change the multiplier. Remember I talked earlier about how the multiplier might be, say, by 4 or something like that. Well, if you increase the multiplier, then of course you can get supposedly at least better performance, but you do also, again, take the risk of increasing the instability of the system and the heat of the system. For example, you can't really see it, but if I scroll down, it goes to by 8. I decided just for fun to go to by 8, and when I did that, it would blue screen every time I tried to start up the computer. So it just couldn't handle it for some reason. There was something in there that messed it up. People that are really really committed to tweaking all of this stuff, these overclockers, they could probably figure this out if they wanted to go into this and really fiddle around. There's a lot of trial and error in this. So for example, if I wanted to go by 8, I would go there, but then it might be blue screening because there's some of these other settings that need to be synchronized with that by 8. I might need to increase the CPU voltage or something. So there are a number of other factors that in overclocking that you go through, but the main thing with overclocking is that we use the multiplier to improve the performance of the processor. And then to continue our discussion of CPU technologies, and again, some of this is a review from things I've already discussed with you, but remember, we have cache, level 1, level 2, as well as level 3. And we have the voltage regulator module. If in a two-processor situation or a multi-processor situation with more than one processor on the motherboard, you might need those to regulate the voltage between the two processors. And in a single processor situation, then that circuitry is going to send a standard voltage level to the processor. And there's actually some communication that can take place with the processor where it can send back information to the voltage regulator module requesting a specific amount of voltage in order to perform the tasks at hand. And also be aware of the fact that the speed might not be exactly the same between two different processors, even though they might both say on the package, 4 gigahertz or whatever the number is. There are a number of reasons for that we've already discussed. One of them might be the size of the cache or the performance of that cache. Another thing might have to do with the clock multiplier on the motherboard. Maybe one of them is multiplying by 4, one of them is also on a motherboard that's multiplying by 5. So of course the one that's multiplying by 5 is going to give you a better performance in most cases. All other things being equal. And also, there's a clock signal that's sent from an oscillator on the motherboard, which is kind of the metronome of the motherboard. And the CPU is capable of splitting that clock signal into multiple signals for its own use. So even though it might be operating at 4 gigahertz, it might be able to split that timing up multiple different ways and to maximize the performance out of it. So a lot of factors go into the speed of things. And right now, it is quite frankly, for my purposes, for general business purposes, most processors are way too fast for me right now. I would be wasting my money to go out and buy the latest, greatest processor to read email and to run Microsoft Word and to record videos like this. It's just nowhere near going to really maximize it. However, on one of my machines, I really do have to get a higher performance processor because I run a lot of Photoshop. I'm a photographer. I do quite a lot of that. I have to have heavy intensity discs, high-speed discs and everything. So sometimes it's a little bit more of a factor than at others. But it all goes according to what the customer's needs are. Then there's also the discussion of 32-bit and 64-bit. We again have already discussed that as well. But when it comes to satisfying the requirements of your customer, you almost always, at 32-bit, you're going to have a high level of compatibility. At 64-bit, like I said before, you'd have to get drivers that are 64-bit, and this can really get to be a problem. For example, I've got a compact laptop that has a 64-bit AMD processor in it. Guess what? It came installed with Windows XP 32-bit edition from Compaq. Why in the world would they do that? Then later on, I upgraded it to 64-bit, and I said, well, surely, since they sold me a processor in this laptop that's a 64-bit processor, they're going to create 64-bit drivers. Wrong. 2 years later, still no 64-bit processor. So I don't know. I really don't get any benefit out of that 64-bit processor. And sometimes you just have to connect with what the customer needs and what the product can actually deliver, whether they have the drivers that are necessary. And there's one more thing here as well, and that is the applications. Even if I install the current version of Office on a 64-bit version of Windows running a 64-bit processor, well, guess what? I'm going to be running Office at 32 bits because there's not a 64-bit version yet. So again, I'm not really getting the maximized potential out of that 64 bits. It's not going to be until applications are 64-bit and the drivers are readily available at 64-bit that we'll really be able to enjoy the full performance of it. In the meantime, the main advantage for 64-bit is that I can also install a 64-bit operating system on that computer. And all of the operating system functions will take place at the 64-bit level, so any of its functions will perform very, very fast. And then finally, before we conclude our discussion of processors, let me also point out the different form factors for the processor package. Here we notice that there's no square location where it has a bunch of pins in it for a processor. That's because this is an older version of a motherboard. Notice that it even has an ISA slot or an ISA slot over here. And with this particular type of a motherboard, it accepts a processor that goes in a slot like this. I used to have one of these many years ago. And the processor that you might see for this might look something like this. It's a card-edged connector. These used to be known as single edge contact cartridge, or SECCs, or SECC2s, which is just a version 2 of the same thing, or a single edge processor. If you were working with an AMD like we see in this picture here, then this would have gone into what we called slot A, and you can kind of equivocate AMD processors go into slot A. They both have A in them, so you can kind of match them up that way to make it easy to remember what goes where. And as long as I'm on that topic, if you do have AMD processors that are more the kind that we're used to seeing these days, which are flat and have pins on the bottom, much like this Intel processor here, a lot of the AMDs have a similar look like this with the pins on the bottom, well, those go into socket A of some kind. Again, socket A for AMD processors. Now, that's not to say that AMD processors can only go into socket A or slot A. They can also go into socket 462 and certain other types. But anytime you see an A, that's always going to be an AMD. Now, the next thing you might be thinking is, James, I've heard of all different kinds of things. Socket 4, socket 7, socket 8, socket 478. Do I have to memorize all these sockets and exactly which processors go in there and exactly how many pins are on the bottom of each one of these processors? No. In my experience in real world, you don't memorize all of that stuff. What you do is if someone brings in a computer to you and they say, hey, the processor is kind of old, I'd like to see what I can do to upgrade it, I look at the motherboard manual or I download the motherboard manual and I look it up. I don't happen to know off the top of my head all the processors that can go into that exact motherboard. There are way too many combinations to make it humanly possible to memorize all of this stuff. Now, this kind of processor is much more common than this older kind right here. These are generally considered defunct nowadays. You'll still get some customers that'll bring those in, but for the most part, we're instead going to have something that works on a pin basis like this or a land grid array basis. First of all, let's talk about the kind of sockets and corresponding processors that you'll have. You'll have a pin grid array or a PGA, and that will be lined up where you'll have pins lined up pretty evenly, better than I'm drawing them here anyway. And you'll have another set of pins that are parallel to the first set of pins, and so on, all the way across, and that would be a pin grid array. However, on some processors, our form factor is getting smaller and smaller, and yet we're fitting more density into them, so we might need to instead have a staggered pin grid array, and with a staggered pin grid array, we start off the same with a row of pins, but then we have another row of pins that's staggered, not directly parallel, but in between the first row. And that allows us to get a higher pin density than we would have been able to otherwise. So that's the staggered pin grid array. And then finally, there's something called LGA, or land grid array. That's going to be the most common type that we'll see for any new processors that are out. And the advantage of that can probably be obvious. Here we've got pins that stick up. Eventually, I'm sorry, but you're going to drop one of these sometime in your career, and it's going to really ruin your whole day. Because it's going to bend a pin back, or it's going to ruin the whole thing. But it could bend a pin back, and you'll have to straighten it out. It always gives you an uneasy feeling to have to mess with these, because these are one of the most expensive parts of the entire system. Or you'll put it accidentally, just absent-mindedly or whatever, not put it into the socket correctly, and something might get bent over or ruined that way. So these pins kind of make me nervous. But the land grid array, instead of using pins, instead it uses lands. And let me just take a look at a profile view of a processor. And here's a look, a side view of the processor. And in the past, of course, we've had these pins sticking up. Well, now instead of pins, we're using lands. So it's just a metal contact here, usually they're kind of a rounded contact here, and they'll correspond with a location on the motherboard's socket where they'll directly make contact in that socket. And there will be kind of a housing that flips over the top of this and that presses down on top of this to make sure that there's good contact with all of these lands. And then beyond that, it also uses a lever, much like we use with a PGA or an SPGA, and like I've shown you in previous nuggets. In this nugget, we talked about CPUs, and we started off by talking about various parts of the architecture, such as the I/O control unit, the control unit, the ALU. Remember, that's the arithmetic logic unit, which is the main function of the processor. Registers, cache of different types. So we looked at all of those things, and then we also identified various characteristics of processors, because it's important to understand these two things in order to understand what a user might need if they want an upgrade to their system. So we discussed that, as well as the various technologies that are available with processors these days, particularly things like CPU throttling, hyper-threading, microcode such as MMX, overclocking, all of those kinds of things we discussed. And finally, we capped it all off by taking a look at some of the kinds of sockets that you might see out there. Remember, slots aren't used so much anymore, and you don't have to memorize every conceivable type of slot or socket that's ever been in use, but you should have a basic understanding, at least, of how they work. And again, remember that nowadays we mostly use the land grid array. Well, I hope this has been informative for you, and I'd like to thank you for viewing.